USA, at Microsoft Research Laboratory for approximately 5 years. So he will tell us many puzzling things about self-organizing cellular automata. We all enjoyed his presentation of open problems in the open session. No doubt that he will again puzzle us with interesting problems. Please, Alexander.
Okay, well, thank you very much. It's really wonderful to be here. So I guess I am a little bit of an outlier with regard to the topic of this workshop, and in particular the thing I'm going to talk about is even a slightly unusual direction for me as well. It's just something I became interested in fairly recently, so it'll be very different from everything else we've been hearing, but I hope at least I will entertain you.
Probability?
There will be probability, yes. You were worried for a second. So it's joint work with Janko Gravner at UC Davis. Papers on the archive. Okay, so I'm actually going to start. I don't usually do this, but I'm going to start with a fair bit of background and motivation. Some people might say waffle, but before I really get to the actual results. And the reason I'm doing this is because the motivation for what we're doing may not be clear otherwise, and I want to make it clear. So let's talk about cellular automata. So they have really distinguished history, going back at least to von Neumann and Ulam, even though perhaps more recently this subject acquired a slightly negative reputation, which is maybe unfortunate. So probably the most famous example of a cellular automaton is Conway's Game of Life, which I expect many people have heard of already. So it's a very simple model. You work on the square lattice Z2, and each cell has two possible states, 1 or 0, alive or dead, and you start with some configuration on Z2, and then you update in discrete time according to a simple rule, and the rule is a 0 becomes a 1 if it has at least if it has exactly 3 1s as neighbors, and a 1 stays a 1 if it has 2 or 3 living neighbors, and neighbors here refer to this 8 neighbor set here. Not that the details particularly matter. So you just you update everything simultaneously in discrete time according to this rule.
And nobody dies.
Well, yes. Cells do die because you. I mean, if you're alive, you stay alive if and only if you have 2 or 3 neighbors. So if you have 4 neighbors, you die. So here's a configuration. If you apply one step of this dynamics, you get this, and of course you keep on applying the same rule, and here's what happens in this particular case. So this configuration is called a glider, so it moves northwest with some repeating pattern of configurations, and there's a whole industry of people engineering life configurations to do interesting things by combinations of gliders and all sorts of other bits. So this is a configuration that someone designed which computes twin primes. So if I run it, all sorts of complicated things are happening, and eventually over here there will be a stream of gliders emerging, and the positions of the gliders in that stream correspond to the positions of twin primes. So not known whether there are infinitely many, and thanks to an extraordinary algorithm called hash life, you can run it incredibly fast. So we're already up to like 1 million generations or so. But of course, this is, as I say, starting from a very, very specific, carefully engineered configuration, initial configuration. So what happens if you make a small change to the initial configuration? So here, this was the initial configuration, but I changed one cell somewhere around here. So let's see what happens if we run this. So, well, somehow I have no idea what it's doing anymore, but it's definitely not computing twin primes. It's just crazy and unpredictable in some sense. Not a big surprise, of course. So, and this is sort of part of what I want to get at. I mean, making cellular automata do interesting things with specific configurations is all very well and fun and so on, but it would be nice to know what happens typically from typical configurations in some sense. And it turns out almost all the interesting behavior that one can observe with these kinds of models happens even for one-dimensional rules. So that's what I'm going to focus on. And I'll make a few basic assumptions. I'll assume there's a quiescent state called 0, which means that if you start with all zeros, then you continue with all zeros. And I'll focus on starting from a seed, meaning starting from a configuration with finite support. So I have zeros everywhere with just a finite number of non-zeros. And especially I'll be interested in typical seeds, which for me means random seeds. Okay, so let's have a look at the kind of things we're interested in. So, so some rules, cellular automaton rules, are completely predictable and easy to understand. Here is one example, the so-called 1 or 3 rule. So it's a one-dimensional rule. The states are 0 and 1, and the new state of a site is 1 if and only if, when you look at its previous state and the previous states of its two neighbors, there are either 1 or 3 ones amongst them. So we normally draw pictures with time going down the page. So here's a picture. So you become black if and only if of yourself and your two neighbors above you, that either one of them is black or all 3 of them are black. And another way to say that, of course, and this is the key to why this is a very easy to understand model, is that you can write that as just the sum of these 3 states modulo 2. Okay, so what does this model do? So here's what happens if you start it from a single occupied cell, a single 1 at time 0, and again time's going down the picture, so each horizontal line is a time step. So you get this nice picture, some sort of self-similar fractal, and this can be completely understood. There's a recursive description of it, and you can answer almost any question you like about this. There's a simple way to compute the state of any cell a long way down without computing everything in between. So that's starting from a single 1. So what happens if we start from a different seed? So here's a random seed of length 10 or something. And then the picture's sort of similar. You still see the same fractal-like structure, except it's thickened by a certain amount. So you still have these triangular voids, but the fractal is thickened. And it turns out in these little necks in between the white triangles, you always see the same local pattern. So this is a phenomenon that's called replication, because you essentially just keep on seeing the same local configuration again and again. It's like reproducing. And again, this can be proved. So any seed for this particular model does essentially this. And for this model, the reason is very simple. So it comes from the additive structure of the rule, this fact that the function telling you the new state is a linear function. It's the sum of these 3 things modulo 2. So a consequence of that is if you want to know what happens starting from any initial configuration, say the one consisting of these 3 sites here being 1s, then all you have to do is draw the fractal triangle starting from each one of those, superimpose them, and then add them modulo 2. So that's all there is to it, essentially. On the other hand, you only need to change the rule slightly for completely different things to happen. So here's an example, rule 30. This is Wolfram's numbering scheme for rules. but it's just some simple rule. I mean, here are the pictures, but the details of the rule don't particularly matter. So here's what happens with rule 30 if you start from a single 1. So totally different, and in some sense it's chaotic, meaning at least if you want to know the state of a cell, well, way down here, no one knows any better way than to compute the whole thing, essentially. But I mean, already you can see it's not quite as simple as that, because along the left-hand edge here, there's some periodicity happening. So, but anyway, it's much more complicated picture. And if you, not too surprisingly, if you start from a different seed like this, you get a qualitatively similar picture, apparent chaos. Well, some of this complexity can be proved rigorously. So, in particular, some cellular automaton rules have been proved to be computationally universal. In some sense, as complicated as you can be. A particularly famous example, Rule 110, which is another of these simple one-dimensional rules, is Turing complete. So, conjecture by Wolfram, proved by Cook. So you can simulate a Turing machine in it. But again, let me just emphasize, what this says is if you start in a very, very particular engineered configuration, then you can simulate a Turing machine.
Sorry, what exactly was this said? And you can find such initial states that it will be arbitrary Turing model, something like that.
I'm not sure what a Turing model is. So Turing machine.
Arbitrary Turing trajectory.
Yeah. So, well, I mean, a Turing machine with a particular initial tape and particular states, you can encode it in the model, and it'll do whatever the Turing machine does. With a sort of a simple coding backwards and forwards between the Turing machine and the automaton. Okay, so in some sense they're arbitrarily complex. In some ways, the most interesting rules, though, are ones which are capable of more than one type of behavior. And one example is so-called exactly one cellular automaton, which is, again, you look at the 3 guys above you, yourself and your 2 neighbors, and if you see exactly 1 amongst them, then you become a 1. Otherwise, you become a 0. So here's what that does, starting from a single 1. Again, nice fractal replication, a different fractal this time. Here's what it does starting from a different short seed. Again, it's nice fractal replication, although it's a little different because the pattern here is different from the pattern here. However, from certain other small seeds, like this one, you get apparent chaos, or at least certainly not replication. And on the other hand, you can cook up initial seeds where you get different behavior again. So periodicity, horizontal and vertical periodicity, is all from the same rule. And you can even cook up or find seeds which give sort of strange mixtures of these behaviors. So here it's apparently chaotic in some cone and periodic in some non-trivial wedges at the edge. So rather surprisingly, some of this can be proved. So Grabner and Griffith recently proved for this particular rule that all these types of behaviors, replication, periodicity, etc., do occur for infinitely many initial seeds, even exponentially many seeds of length L. And they conjectured, moreover, based on a lot of empirical evidence, a very natural thing that since, well, I won't say since, so this model is capable of chaos, apparently, and the conjecture is that chaos is typical, meaning that if you start from a uniformly random seed of length L, then with high probability you have chaotic behavior, at least within some wedge. Now, what does chaos actually mean? So this is a bit of a problem with this subject because there's no universally agreed definition of what chaos should really mean. But at least, I mean, one specific thing you could say is something like, if you look at local patterns, and if you look at how often you see any particular local pattern in space-time, then those things should converge to a consistent probability measure. Those densities should converge to a probability measure, and it should be a probability measure with some sort of spatial mixing property. So things a long way apart are independent. I mean, it's maybe not not all you would want from a definition of chaos, because somehow there's this feeling that it should be unpredictable as well, but at least that's something concrete. But nothing like this is proved for any cellular automaton, essentially. But that's the conjecture. So now, one difficulty with this subject is there are very few general principles somehow, and you might think here is a possible general principle that if some cellular automaton rule is capable of producing chaos, whatever that means, from some seeds, then chaos should be the norm, in the sense that almost all seeds should yield chaos, almost all long seeds, let's say. And that's a very natural thing to guess somehow, because the picture one might have in mind is that there's some perhaps rare event, rare local configuration, which when it happens generates chaos, and the chaos takes over. In any battle between chaos and something more ordered, the chaos should win, sort of analogous to the second law of thermodynamics. And indeed, this appears to be the case for many models people have looked at. So, but, well, that is not always the case. So yes.
Can I just throw in something? Yeah. The rules you're giving are sort of just kinematical. So when I use the word thermodynamic, I have in mind an energetic structure. There's some other component that's required before I want to use the term thermodynamics.
Of course. Mm-hmm. Yeah.
So what sense do you use it here?
Just by analogy. I mean, yeah, it's a weak analogy. I mean, just the idea that chaos should, or disorder should eventually triumph over order. I mean, nothing. Yeah, I'm not trying to make any deeper connection than that.
But I guess what I was sort of hinting at is whether or not there are cellular automata models which are in fact energetically driven, that there's some underlying law and a free energy associated with it, and then organization happens around that.
There certainly are, yes, but I'm not focused on that. Yes. So, well, yeah. So turns out this is apparently not a general principle. So Grabner and Griffith conjectured again on the basis of strong evidence that for certain one-dimensional rules, indeed ones that are interesting for other reasons, some exceptional seeds yield chaotic behavior, but typical long seeds yield ordered, predictable behavior, and in a non-trivial way as well. So somehow order wins. And what we're trying to do is prove a rigorous version of this. And now I want to sort of be careful at this point, because this subject of cellular automata is somehow filled with all sorts of overblown claims involving many of the words on the slide. And I don't want to fall into that same trap. So I mean, what we prove is just something very specific about some very specific class of models. But my goal in this first 10 minutes was to try to make the point that our motivation comes from some really quite deep questions, even if they're not mathematical questions necessarily. Okay, so this is where we're coming from. And I should briefly mention a somewhat related thing in spirit is this celebrated or notorious positive rates counterexample. So there's a result of Gatch saying that there is a one-dimensional cellular automaton rule, so that basically if you add noise to it, it's resistant to noise. So it's a one-dimensional rule, but you introduce some random errors to it. At each step you make an error with probability epsilon in each location. And it's possible to construct one with multiple stationary distributions. So that essentially means it can retain information forever, even though you have these errors happening. In 2 dimensions, there are plenty of models that can do that, but here the claim is there's a one-dimensional model. Now, unfortunately, this is an exceptionally difficult proof, over 200 pages. I think it's fair to say that no one other than the author understands it. So it's an exceptionally complicated construction as well. And what we're doing will not be in that category. Yes?
So you're saying that when the random error rate is not there, you have the same distributions? Or the random errors are generating the distributions?
Well, it won't be the same distributions because I mean certainly the errors allow different transitions to happen. So once you introduce the errors, it's a Markov chain, and we're looking at stationary distributions of that Markov chain. So they're not going to be identical to what happens without the errors.
So I guess that my point is the robustness of the observable distributions under perturbation.
Yes.
A family of distributions, one for each epsilon?
Well, yeah. I mean, it's certainly when you change epsilon, you're going to change the distribution. I mean that's a triviality because just locally different things can happen. But you should think of. I mean, imagine something like the Ising model, where in 2 dimensions you have a plus phase and a minus phase, but the exact nature of the phases depends on the temperature. So it's analogous to that. And again, I mean, in 2 dimensions, the Ising model is in some sense an example of something like this, but the key here is it's a 1-dimensional model, so that's the big deal. Okay, so I won't say any more about this, but it's sort of the same sphere of ideas motivating it, I guess.
Sorry, the radius of interaction now, what is the radius of interaction?
In gaseous,
Yes.
well, you can take it to be 1. I mean, you can either take a huge number of states and interaction radius 1, or you can alternatively bring the number of states down and make the interaction radius bigger. It doesn't make any difference.
But your alphabet is 1 and 0.
No,
No.
trillions of states.
So now your alphabet is very large.
Yes, if you want the interaction radius to be 1, at least. Astronomical. Right, okay, so here's what we did. So for a certain class of 1-dimensional rules, started from a uniformly random seed of length L, and the limit as L goes to infinity. You have replication, with high probability. I'll tell you what that means. While some seeds for the same models yield provably more complex behavior, and some apparently yield chaos, although no one's managed to prove anything like this last statement. So, of course, for this to be a theorem, I have to tell you what these things actually are. So let me do that. So, first of all, we prove things for a whole class of models, but here's the simplest one in our class. Maybe you have 3 states, and don't bother with the formula. The idea is that if you ignore the difference between 0s and 2s, then you see the 1 or 3 cellular automaton that I started with at the beginning, this nice, well-behaved additive one. So that's the black and the white here. And then the state 2, the red ones, they perform 2-neighbor XOR on the spaces left by the 0s and 1s, so on the 0s. Okay, so it's just a rule. So here's what that rule does, starting from 1 seed. So I guess this is very faint, but can you see the 2 colors here? There's some gray here. So this is an apparently chaotic evolution from one small seed, and here's what happens for a longish random seed. And so again, it's probably hard to see, but in here you have this nice, well-behaved fractal with these triangular holes, and you only have red around the edge. So the theorem will say typical seeds behave like this. And here's another example of the evolution of the same rule. So this is something called quasi-replication, which I'll define in a minute. So it's not replication, but so it's more complicated than replication, but you can actually describe it rigorously. And here's another example of quasi-replication. So another more complicated behavior than what the theorem says happens typically. Okay, so what's replication? Here's a definition. So take the nice fractal, so simply the support of the 1 or 3 cellular automaton, this very nice one starting from a single alive cell, that's the nice fractal, thicken it by distance r as a set in R2 or Z2, and we say the configuration is a replicator of thickness r and eta if every bounded component of the complement of this thickened fractal is filled with a translate of eta, and eta is some doubly periodic configuration of zeros and twos. So the picture is something like this. You have the nice fractal, and within each triangle, if you come away from the edges by some fixed amount, you just see some periodic pattern. Okay, that's the definition. And incidentally, this is work by Grabner, Griffith, and Pelfrey. If you know that, then in some sense the configuration near the fractal is also predictable, because these little necks in between the periodic regions are of bounded size. So there are only finitely many configurations that you can possibly see in those. So with some work, that means you can understand the whole picture if you're in a situation where replication occurs. So this is an example of a replicator with 0 ether, because in the voids of the fractal you just have zeros. This is another rule in our class. It's a replicator with a different ether. You have the thickened fractal, and you have this periodic pattern in all the triangles. And here's the same rule and a replicator with a different ether. So you have different periodic pattern here. So here's another example of a replicator with 0 ether. You can have various things happening in the fractal. And this is not a replicator because we have a different ether here and here. Okay, so the middle part of my theorem says if you start with a random seed, then there's some random distance, but which is nevertheless tight as L goes to infinity, so that you have a replicator of thickness that distance plus L and a random ether with high probability. I mean, the way I've stated it here is if R is infinity, then you don't have a replicator. And what's the class of cellular automata we work with? I won't give you a formal definition, but the idea is similar to the one I showed you. You have 3 states, and if you ignore the difference between zeros and twos, then you just see the 1 or 3 cellular automaton rule. So you can imagine you do that first. You apply this nice additive rule to 2 zeros and 1s, and then there's some condition about the information about the distinction between zeros and twos. So you think of the twos as living in the spaces left by this, but they can only, information about twos can only pass along certain types of path. So they can only pass along diagonal paths, but by which I mean you can move 1 step southeast, or you can move 1 step southwest. And we can also prove a similar thing for wide paths, which is paths where you can go in any direction down, but you're not allowed to move between 2 ones. Okay, so don't worry too much about this definition. The theorem applies to all such rules. And what's this provably more complex behavior? So, okay, this is a definition due to Grabner, Griffith, and Pelfrey as well. You say that a configuration is a quasi-replicator if there's some fractal set, basically, so some exceptional set in Z2 which has a scaling limit which is a non-trivial fractal, has non-trivial Hausdorff dimension, so that each component of the complement of that set is filled with some periodic ether. So it's an extension of the definition of replicator. And the rather amazing thing is that in many examples you can actually prove that specific seeds are quasi-replicators. So this is an example that I showed you before. So here this exceptional set is the grey and the red. That has a fractal scaling limit. And so here it's not difficult to imagine that you can fill this particular seed. You can just analyze inductively everything that happens, and you can prove you have a quasi-replicator. And in this example, you can as well. It turns out there's an inductive scheme where you can completely analyze this picture starting from a single seed. It's some work. That's a bigger picture of the same thing. This is an example of another quasi-replicator. So you have this ether, but you have these little disturbances in it, and these disturbances are on a fractal set, essentially. And you can prove that for this particular case. On the other hand, here's something which looks superficially similar, but we believe this is chaotic. Okay, so this last part says, for the same rules, typical seeds yield replication, a simple behavior, while some exceptional seeds yield quasi-replicators, which are not replicators. And again, some apparently yield chaos, but unfortunately we don't know how to prove that. And we can prove various additional things. So in particular, these ethers, which are these periodic patterns you see in the void, if basically any ether which you can see for some seed, you will see with positive probability in the limit. So I showed you that the picture of this, the pink picture where you had two different periodic patterns are going for the same rule. So any, in the limit as L goes to infinity, you just have replication, and if it's possible to have different ethers, then they will all be represented in the limit as L goes to infinity. And well, we proved various other things, like with high probability, the influence of zeros and twos in the initial configuration doesn't have much effect. So I probably won't have time to say much about this, but the rules that I'm looking at, they may seem rather contrived, and in a certain sense they are, because they're just the ones that we managed to prove this for, but they include some very useful ones. They include rules that can be applied as tools in the study of two-dimensional cellular automata that people really care about via something called boundary dynamics. So you're interested in some two-dimensional growth rule, and you think about what happens on the boundary, and that's described by a one-dimensional rule. So I don't have time to get into it, but there are some applications in that direction. So all right, so the key tool for all this is something rather simple, and another of my favorite subjects, percolation. Here's a key result. So let's just think about this 1 or 3 cellular automaton. So again, this is the nice, friendly, additive rule. You become a 1 if you see 1 or 3 1s above you. And let's think of it started from a uniformly random configuration on the whole of the line, Z. Fair coin flips, zeros and ones. And we look at paths. So we look at diagonal paths, empty diagonal paths, which again means, so here's a configuration of the 1 or 3 rule, and you look at paths which live on the zeros, on the white, and which are allowed to take steps this way and this way. Okay? And it says those things don't percolate, and moreover you have exponential decay for the probability that you reach down a certain distance. And similarly for wide paths, which again were ones which live on the zeros and which can go down or diagonally down, but they can't squeeze in between two ones diagonally. And on the other hand, it's not true for all types of paths. If you just look at empty paths where you're allowed to go down or diagonally down, then they do percolate. So with positive probability, there's an infinite empty path from, yeah, I should have said, by the way, the pictures, I guess it's obvious. These are all the points you can reach using diagonal paths from this blue interval, and here, and here's the same thing for empty paths. So empty paths percolate, the other two don't. So how do we prove this? Well, it's a highly dependent percolation model, right? It's nothing like ordinary IID percolation at all, because all the randomness is in the initial configuration, in the initial top row. The rest of the configuration is simply a deterministic function of it. So it's nothing like ordinary percolation in a way, in general, these highly dependent long-range percolation processes can be very, very challenging to analyze. There's some relevant papers here, but in some cases we're lucky and they're sort of amenable to analysis, and this is one of those cases, and there are a number of other examples in that category here. So here's the basic method. It's really linear algebra. Don't bother about the formula. Here's the idea. We're considering the 1 or 3 rule, and we suppose that the initial configuration is uniformly random on some set of points, maybe deterministic everywhere else, and then we're interested in some space-time, some set of space-time points down here, and we want to we're able to say under certain circumstances the configuration in the space-time set down here is uniformly random. It's fair coin flips, just restricted to that set. Okay, and how do you do that? Well, by the linearity or additivity of the rule, the configuration that you see here is a linear function modulo 2 of the initial configuration. And basically we look for cases where the linear map from here to here is an upper triangular matrix with ones on the diagonal. If you find such a case, if you think about it, it means that the configuration down here is exactly fair coin flips, restricted to that set. Okay, so that's the basic technique. And once you have this, it's just a matter of sort of trying all the percolation arguments that you can think of until maybe you find one that works, but most of them don't. But so here's, for example, how you prove that empty paths do not percolate. So if you look at, empty diagonal paths. So here's a diagonal path. The number of paths of length t starting from a point is 2 to the t. And it turns out the probability that any given diagonal path is empty is exactly 2 to the minus t, exactly as it would be if the whole thing was IID percolation. And why is that? It's by what we call dual assignment, this linear algebra thing. The basic idea is if you explore the path going downwards, every step you take, there's a new random site in the initial configuration that you can look at that you haven't looked at before, which affects that bit. So the probability that they're all zeros is exactly 2 to the minus t. Now, of course, this isn't quite good enough because this is just 1 over this, so this is sort of a critical percolation picture, and we want to prove it's subcritical. So we have to look for a way to squeeze something more out of it, and here's what we found. If you look at a leftmost diagonal path, then you know that, well, whenever it makes a step to the right followed by a step to the left, then the site that it didn't visit must be a 1, and that enables you to get a bit more information, and it turns out you can add a little bit extra to the exponent here for the number of these corner sites. And the key fact here is, I didn't say on the linear algebra slide, but to make arguments like this, the matrix of the linear map is basically described by the fractal, the configuration starting from a 1. So the key fact here, it turns out, is that in this nice fractal, the diagonal 1 off the edge is alternating zeros and 1s. That's what makes it work. So that's the kind of technique. No percolation for wide paths and percolation for empty paths use sort of superficially similar ideas, but different in all the details. So here's how you can use this kind of thing. For example, so this was all starting from uniformly random configuration on the whole of Z. So now what I want to do to prove the theorem is think about a uniformly random configuration on a seed, on a finite interval. Now this sounds much harder because there's much less randomness. Right? There's only finitely many bits of randomness available. So how we use it. So first of all, here's an example of the kind of thing you can prove. If you start from a seed of length L, then with high probability there's no empty path from the initial configuration into the sort of light cone of the seed more than distance about log L. So diagonal paths don't penetrate into the interior of this triangular picture that you get. And the idea is here we actually exploit the long-range dependence. The point is, if you look down the side of one of these configurations, then what you see just along this diagonal is periodic. And it's periodic with a relatively small period. If you take this K, a strip of thickness K along the diagonal, then it's periodic with a period linear in K. And that's only true for additive rules like this one. And furthermore, each row in this diagonal strip is exactly uniformly random. It's like fair coin flips. So basically we can use the result about starting from coin flips everywhere on each row and apply a union bound, and it sounds like we need a union bound over infinitely many events, but no, we only need it over the period of this thing. So the union bound works out. Here is okay, and we have this exponential bound on the bottom. And I won't go into it, but using similar techniques, we get the main term. We show that above each of these triangular voids, there's a periodic strip that you can't penetrate with paths. So therefore, influence about zeros and twos can't get through. And the fact that it's periodic means that it produces a periodic ether in the triangular hole. So I should emphasize here, in some sense it was sort of surprising that we were able to prove all this, because just exactly the things we needed worked, and almost anything else we're not able to prove somehow. So in particular, what I've been talking about is subcritical paths in this setting of space-time configurations of cellular automata, and supercritical paths are not understood well at all. So remember, an example of supercritical paths was what I called empty paths, which is where the paths live on the zeros of the 1 or 3 rule, and you're allowed to go down or diagonally down. So we know, for example, that the frontier of the places you can reach from an interval or a half line has an asymptotic speed, a quarter. That's one thing we do know. But we don't know what happens if you start from a random seed on an interval, for example. This is one thing you would really like to know. If you start from a uniformly random seed on an interval, and you start an empty path from the left-hand side, where can you reach? How far do you reach across? We conjecture that typically you reach within a non-trivial power of the edge. T to a non-trivial power of the edge. However, that's not true for every seed. Here's an example where provably this frontier converges to a kind of double staircase, and despite the similarity between these two pictures, they're totally different. So here in the limit, this is a constant fraction of t, and here it's little o t, apparently. We don't have a proof of this. We do have a proof of that. And understanding this would be really useful to understand some pictures that we don't understand. So here are some examples of cellular automata started from the cellular automata in our class started from various seeds. This one, and this is the one I started with. This is a bigger picture of it, and it seems like the remarkable things that are going on here are somehow driven by one of these power law frontiers. And another thing we have no idea how to analyze are apparently critical percolation paths. So this is an example, I'm trying to talk about it. Okay, and there are lots of open problems. and if you want to think big, here's a question which I think is incredibly difficult, and perhaps we'll never know the answer to it. If you take Conway's life and start it from a uniformly random configuration on the whole of Z2, what does it do? I think that's an incredibly challenging problem, because we know that life is capable of doing incredibly complicated things, but on the other hand, those things can be destroyed by chaotic influence from outside. So which wins? Does the chaos win, or do the organized things win? Maybe even impossible to answer this question. So lots of questions about these particular models. I'll stop there.
Thank you, Alexander. Are there any questions? Very likely, yes. Yes.
So, your theorem was phrased in a way that gave the impression that what you call replication actually corresponded to order. But I got the impression that you actually have to exclude something that you don't understand, right? You see, it's like the complement of a set that you don't have much control over.
No, actually, that's not true. I didn't spend much time on it, but if you have replication, then you can sort of understand everything in a sense, because of this. So if you have a replicator, then these bits have just bounded width, fixed width, so there are only finitely many patterns you can see there. I mean, it's bounded by 2 to the length, but in practice it's much less than that typically. So yeah, there is a sort of inductive scheme of so in principle, in any replicator, there's a formula for what the state of a cell arbitrarily far down, even if you're in.
The other question I had was, what was the point of mentioning Gatch's result in this context? Does it have anything to do with what you did subsequently?
No. So my point is that one can regard it as motivated by similar philosophical questions. So. Is it possible, or when is it possible for order to survive in the presence of chaos?
There's also the theorem of Tomb I remember encountering.
Yes.
How does that relate to the story? That's gives you some criterion for when you have multiple stationary solutions to the set.
Right. Right. So this is also about one-dimensional rules,
and persistence of long-range memory in one.
Right, and it gives conditions under which you can't have it.
It's some kind of convex.
That's right. That's right. I mean, yes. So it's very. I mean, it's
noise-free. I think is what I remember.
What?
It's not in the noisy case. It's as far as I recall.
Maybe
I'm not sure.
Maybe it's something different. I mean, I think there is a theorem by Tomb that. I mean, it's sort of going in the opposite direction of Gatch's result. It's saying under certain specific but quite general conditions for a one-dimensional rule, in the presence of noise, you cannot have multiple invariant measures. But it's not completely general, hence it doesn't contradict Gatch's.
So you think of Tomb as a sort of subset of the complement of Gatch's result? Is that how I'm thinking about it?
Mm-hmm. Yeah, if I'm remembering it correctly.
Yeah, I'm not remembering correctly either, so that's fine.
Are there other questions? Yes.
So these, of course, what makes these problems super difficult is because they're completely rigid given the initial configuration.
Yes.
So they're totally deterministic once the initial condition has been determined.
Right.
So the following question is not supposed to subtract from the power of your theorems, which are very impressive, but a natural thing to do is to lubricate the problem by adding in some extra randomness.
Mm-hmm.
What Gatch did was a rather extreme example of that.
Mm-hmm.
I wonder whether that was an idea which had also found interesting application in this area, apart from Gatch's theorem. There are various ways of introducing extra randomness.
Right. Yeah. I mean, it really. I don't think it's been explored very much, to be honest. And there are interesting questions. So for example, if you just run one of these additive rules, like the 1 or 3, and you introduce just small errors, then the behavior is totally different. You just don't see the fractal anymore or anything like it. You just see noise, experimentally. So I don't think anyone's really explored these things rigorously, and certainly one could. There's very little work that we are aware of on cellular automata started from typical configurations, random configurations. I mean, that's not what you asked, actually, but it's a fact. I mean, there are very specific cases like bootstrap percolation that have been heavily studied, but very little. And I think it's a pity because as I say, generating engineered initial configurations is all very well, but if one wants to claim that these models have anything to do with nature and the universe, then you'd better say what they typically do. But it's very hard.
Yeah, so since some of these models are kind of, as you said before, like universal Turing machines or universal computers, I'm wondering if there's any work at all, or if you've thought about it at all, about the connection between this and like Chiton's work on like the halting probability of like a random computer program or something like this?
Yeah, I'm not really familiar with that, actually.
I'm interested in the dynamical systems view of these models.
Louder, please.
I'm interested in the dynamical systems views of these models. So in the Hamiltonian world, there's been some effort that's been expended on so-called ultra-discrete Hamiltonian systems.
What was it again?
Ultra-discrete. You think of a classical Hamiltonian model, generally partial differential equation. You can discretize space and time, and then you can also discretize the state. If you discretize the state, you essentially have cellular automata versions. And so there's been some effort spent on finding equivalents of classical solitonic behavior in Hamiltonian systems.
Okay.
So you've introduced a notion of time here in this picture, a spatio-temporal structure. I'm wondering which of these cellular automata that you look at can be viewed as having Hamiltonian structure, or perhaps the opposite, dissipative structure, or more interestingly, a bit of both.
I'm afraid I don't know the definition of either, but and so therefore we haven't looked into it. But it sounds extremely interesting. I'd like to hear more about this.
Alexander, I have a small question, just a technical question. You said that when you start from a finite configuration, random configuration on 0L, it is more difficult than when you start from an infinity. Could you comment from a probabilistic or mathematical point of view? Why is it more difficult?
Okay,
I don't see it at once.
I said what I meant to say was a priori it might appear to be more difficult because I mean, as Jeffrey alluded to in his question, what one seems to find in practice is that more randomness is helpful because it provides lubrication. Right. So if the difficult things to analyze are things where you have only a little bit of randomness and then the evolution is deterministic and rigid.
But the evolution is deterministic, as you say.
Right, but yeah, well,
okay.
I mean, as I said, we were able to analyze it, and it involves this nice interplay between you have enough randomness that you can find these sets where things are uniformly random, and on the other hand, you have this exact periodicity, which is very deterministic. It's the opposite of randomness, and by playing these against each other.
Let us think again.